Hello and welcome. We're continuing our video lecture on section 4.2. We finished with this slide on the last video. So we're looking at randomization distribution, which is a collection of statistics from samples simulated assuming that the null hypothesis is true. So we're going to be doing this really the rest of the semester. If the null hypothesis is true, how extreme is the data that you collected? So the randomization distribution shows what type of statistics would be observed just by random chance, assuming the null hypothesis were true. So one way to think about it is we're going to assume the null hypothesis is true to try to see if it's not true. It's kind of a strange logic. We're going to assume the null hypothesis is true, and if your sample data is so extreme, then that's evidence that the null can't be true, that your sampled evidence that you did collect is just too extreme. So let's go back to the green tea. The slightly different experiment with green tea, but looking at prostate cancer. So a study was conducted on 60 men with a prostate cancer, pin lesions, some of which turned into prostate cancer. Half of these men were randomized to take 600 milligrams of green tea extract daily. The other half were given a placebo pill. And the study was double-blind, so neither the participants nor their physicians or doctors knew who was receiving the green tea versus the placebo. After 1 year, one person that was taking the green tea supplement got cancer, while 9 were taking the placebo did get cancer. So I think 1 out of 30, they split this into 2 groups, got cancer, and 9 out of 30 that were taking the placebo got prostate cancer. All right, the explanatory variable is green tea extract of the placebo. The response variable is whether or not the person developed prostate cancer. What statistic and parameter is most relevant? All right, in other words, what are we looking at here? We're looking for difference in proportion. We're looking at 2 categorical variables. We're looking at whether you took green tea or placebo, and then whether or not the person developed prostate cancer. The 2 categorical variables, so we have a difference in proportions. So we're going to let P1 be the proportion of green tea consumers to get prostate cancer, and P2 be the proportion of placebo consumers to get prostate cancer. So which one of these 4 would be the null hypothesis? Hopefully you guessed A. Because the null hypothesis is always a statement of equality. So there should be a statement of equality. Now, what would be the alternative hypothesis? And think about the evidence. Where only 1 out of 30 of the green tea consumers got prostate cancer, and 9 out of 30 of the placebo consumers got prostate cancer. So the evidence should support the alternative that P1 is less than P2. The alternative hypothesis is what the researchers are aiming to prove and or what the evidence supports, which is both in this case. So in a randomization test, we state the hypothesis, which we just went through, collect the data, which was done for us already in a past experiment, calculate the statistic. Okay, so here P1, this is 1 out of 30. This P1 is those that took green tea, and the P2 hat is 9 out of 30. So we subtract these 2 to get minus 0.267. We're going to simulate statistics that could be observed just by random chance. Again, assuming the null hypothesis were true. And then we want to know, well, how extreme is this data point on the simulation? So here we did our randomization via stat key, 1,000 different samples. So notice up here, group 1, there's 1 out of 30 that developed cancer. That's the green tea group. And then 9 out of 30, this is the placebo group, developed cancer. And the difference is minus 0.267. And keep in mind that center is 0. We're always assuming the null that P1 equals P2, or the difference between these 2 is 0. So that's why 0 is the center of the randomization distribution. And based on the randomization distribution, would the observed statistic minus 0.267 be extreme if the null were true? And the answer to that is yes. We look at this data, where would 0.267 be? It would be way over, actually off the screen. Minus 0.267 would be somewhere over here. So fairly far from the center of this distribution. So with this, do we think the null hypothesis is a possible explanation for these results? I would argue no. That 0.267 is just too far away. It's too extreme from the null hypothesis. So this would be some evidence that the null is false and the alternative is true. That green tea does seem to help these cancer rates, at least with prostate cancer. So if we're doing a hypothesis test for H naught is mu equals 12, or we're assuming the mean is 12, and the alternative is that the mean is less than 12. And suppose we have a sample of 45 data points, and the sample average is 10.2. What do we require about the method to produce randomization samples? Kind of a strange question. Maybe another way to say this is, what are we going to assume is true to produce a randomization sample? And we're going to assume the null hypothesis is true to generate randomization. And then where will the randomization distribution be centered? 10.2, 12, 45, 1.8. Well, we're assuming the null hypothesis is true, so we're assuming the center should be whatever the null is. And the null is 12. All right, randomization distribution simulates samples, assuming the null hypothesis is true. So randomization distribution is centered at the value of the parameter given in the null hypothesis. So if this is a difference of means, it's going to be 0. Otherwise, it's going to be whatever that parameter states. So going back to this hypothesis test, the mu is 12, and the alternative is that mu is less than 12. And the sample data of 45 gives us a sample mean of 10.2. And what we look on the randomization distribution? Do we want to know how extreme 10.2 is, how extreme 12 is, how extreme 45 is, what the standard error is, or how many randomization samples were collected? If we're testing this null and alternative hypothesis, we want to know how extreme the sample data is. How extreme is 10.2 relative to the null hypothesis? All right, let's look at another example. If we have a hypothesis test, H naught, the null hypothesis is that mu1 equals mu2, and the alternative is mu1 is greater than mu2, and we have a sample with x bar 1 is 26, x bar 2 is 21. So x bar 1 goes with mu1, x bar 2 goes with mu2, but this is your sample data. What do we require about the method to produce randomization samples? Again, kind of like not required, but what do we assume is true to produce randomization samples? We assume that the null hypothesis is true. We assume that mu1 equals mu2. All right, where will the randomization distribution be centered? All right, here we're not given it directly. We need to assume mu1 equals mu2, but think about this as a difference. The difference between mu1 and mu2 needs to be, or assumed to be, equal 0. We assume the randomization distribution is centered around the null hypothesis, but we have to subtract to make a difference of means equal to 0. All right, in a hypothesis test for mu1 equals mu2, alternative mu1 is greater than mu2, and our sample data is x bar 1 is 26, x bar 2 is 21. What do we look for on the randomization distribution? What's the data point we would look for? We're looking for how extreme your sample data is. So it's not the first two. We want to know how extreme is 26, 21, or 5. And if you think about in the last multiple choice question we did, previous slide, we want the difference of means. So we want to know how extreme 5 is. Well, why 5? 5 comes from, we're subtracting mu1 from mu2 to get the center of 0. So then we want to look to see how extreme the difference in the sample data is. 26 minus 21 to get this 25.